Multivariable calculus, a review for exams. Hello everyone, my name is Rafael, I am an electrical engineer, and in this video I would like to invite you to review with me double, triple, and line integrals as a review for exams. Let's go to the first exercise. Exercise 1, calculate the double integral if R is the region composed of points x, y, if x varies from -1 to 2, and if y varies from 1 to 3. Okay? This is question 1. Let's go to the solution. Okay? As we already know, the interval in which x varies is from -1 to 2, and for y it is from 1 to 3. We are going to apply this interval of integration here in this double integral. So y varies from 1 to 3, and x varies from -1 to 2, and we are integrating 2x squared minus 3y dx dy. Okay, we are going to integrate first in x, and it is going to be the integral from 1 to 3 of integrating in x. We get that the integral of x squared is a third, but we have a 2 here, then it is 2/3 of x cubed minus, here we don't have an x, so an x is going to appear here. It is minus 3xy. Evaluated from -1 to 2. Okay? And to calculate this, we simply put 2 here and here, minus, and then we put -1 here and -1 here. Okay? And then we get that this integral becomes from 1 to 3 of minus 9y plus 6 dy. Alright? When we integrate in x and evaluate from -1 to 2, we get this minus 9y plus 6. Now we have to integrate in y, and integrating in y we get 9/2 y squared plus 6y, and we evaluate this from 1 to 3. We do the same, we apply 3 here and here, and subtract the application of 1 here and here. And then we get the number -24 as a solution of exercise 1. Okay? Let's go now to exercise 2. Exercise 2 now. Calculate the volume of the solid bounded by f of xy equal to x squared plus y squared, and the region of the xy plane where x varies from 0 to 1 and y varies from 0 to 1 also. And let's go to the solution. The volume of the solid is equal to the integral from 0 to 1, the integral from 0 to 1 of x squared plus y squared dx dy. Okay? We could choose to integrate in x first or in y first. We are going to integrate in x first. Okay, integrating in x, we get that it is the integral from 0 to 1 of the integral of x squared is a third of x cubed, plus we don't have an x here, and x is going to appear, xy squared, evaluated from 0 to 1 dy here, okay? What we need to do is to simply apply this one here in the place of x, and here 2 in the place of x. 0, it is not necessary, because if we apply 0 here, it all becomes 0, okay? And by doing this, we get that the volume is the integral from 0 to 1 of a third plus y squared dy. And now we are going to integrate in y. It becomes a third times y plus a third times y cubed, evaluated from 0 to 1. And then we apply 1 here and 1 here, minus the application of 0 here, 0 here. And we find the number of 2/3. And this is the result, the solution of exercise 2. Let's go now to exercise 3. Let's go to exercise 3 now. Calculate the volume of the solid bounded by f of xy equal to 4 minus a ninth of x squared minus 1/16 of y squared, and the planes x equal to 3, y equal to 2, and the coordinate planes. Okay, let's go to the solution. Firstly, we need to understand the intervals of integration. Okay, and what we are integrating, we need to calculate the volume of a solid. Okay, so what is the solid? The solid is this, okay? It is bounded by this plane here, okay? This plane here, x equal to 3. The plane here, y equal to 2. The coordinate planes, here xy, here yz, here xz, okay? And the lower limit is this rectangle here, okay? X equal to 3 and y equal to 2. And the upper limit is the function, okay? See that it is not a prism. This solid here is not a prism, because the lid is curved. The lid is curved in accordance with this function here, okay? So this is what I attempted to draw. Now we know the intervals of integration. X varies from 0 to 3. Y varies from 0 to 2. And z varies from the xy plane to the function. The function is the lid here, the function. And the function is f of xy, all right? And then this is what we need to do. The volume of the solid is the integral from 0 to 3 in x, and from 0 to 2 in y, of the function 4 minus a ninth of x squared minus 1/16 of y squared dy dx. We could have chosen to integrate in x first, but we are going to integrate in y first here. Integrating in y, we don't have a y here, then a y is going to pop up here, 4 times y. We don't have a y here, then y is going to appear here, a ninth of x squared y, and here I have 1/16 y squared, and integrating this, we have 1 over 48 y cubed. And integrating in y, we get the integral from 0 to 3 for y minus 1 over 9 x squared y minus 1 over 48 y cubed, evaluated from 0 to 3 dx. And if we substitute 3 here, here, and here, we get that the integral, the volume of the solid, is the integral from 0 to 3, 47 over 6 minus 2 over 9 x squared dx. Now we have to integrate in x. Okay, when we integrate in x, we discover the value of, we simply integrate in x, we don't have x here, and x is going to appear, it is going to be 47 over 6 times x, and here we have an x cubed, x squared here. The integral of x squared is a third of x cubed, and this third multiplies this to 9th, and then we apply the intervals of integration, and the result of exercise 3 is 21.5. Okay, this is all for exercise 3. Let's go to exercise 4 now. Exercise 4 now. Calculate the double integral of x plus y dx dy, where D is the triangle whose vertices are -1, 0, 1, 0, and 0, 1. Okay? This is what we are going to do to calculate the double integral of this function over this triangle. Analytically speaking, the boundaries of D are f1 and f2, f1 of x and f2 of x, and the x-axis. Alright, we need to express f1 of x and f2 of x in terms of x. Let's find f1 first. f1 of x, we use a general term, ax plus b. We simply use the extremes of the function. We apply -1 and 0 in the function, 0 and 1 in the function, and we get a function of the sort equal to x plus 1, okay? It is easy, I'm going to read it for you. The same is going to be done for f2 of x. f2 of x, we are going to use a general term, cx plus d. Okay, we simply apply the limits of the function. 1 and 0, we apply here. And also 0 and 1, we apply here. And by doing this, we find a function of the sort minus x plus 1, okay? So these are the functions, okay? This triangle has as boundaries the x-axis, f1 of x, which is x plus 1, and f2 of x, which is minus x plus 1. Okay, now that we know the regions of integration, we can divide this. We can divide this from here to here and from here to here. Okay? And we are going to call here D1. Okay? And this region here we're going to call D2. And you're going to discover why now. D1 is the region of the xy plane belonging to R2, in which x varies from -1 to 0. Okay, here is 0, 0 in x. This is the x-axis. In the region D1, x varies from -1 to 0. and y varies from 0 to the function. Here, the function is f1 of x, and f1 of x is x plus 1. And in region D2 is a region of the xy plane belonging to r squared, and x varies from 0 to 1, okay, begins in 0 and it ends in 1, and y varies here from 0 to the function, and in this case, region 2, the function is 1 minus x, or if you prefer, minus x plus 1. And we need to develop this. We are going to have the integral over region D of x plus y dx dy will be equal to the integral from -1 to 0 and from 0 to x plus 1 of the function x plus y dx dy, plus, because we have two regions of integration, we are going to integrate over here and also over here, and from 0 to 1 and from 0 to 1 minus x plus y dx dy. All right, we are going to proceed in the same manner we did before for exercises 1, 2, and 3. And finally, we are going to discover that the integral over d of x plus y dx dy is equal to a third. All right? And this is all for exercise 4. Let's go to exercise 5 now. Exercise 5 now. Find the volume of the solid bounded by the cylinders x squared plus y squared equal to a squared and x squared plus z squared equal to a squared. All right, let's understand it. Let's understand what we are integrating. Okay. Let's draw the cylinders. First of all, let's draw this cylinder here. Okay. This cylinder here along this cylinder here along the z-axis. Okay, and we are going to have a surface here on the xy plane, and the cylinder is going to be like this. Okay, it is not going to be possible to draw the entire cylinder because we are attempting to represent a three-dimensional object in a plane. The board is a plane. It is difficult to represent this, but I think you can have a gist of what it is. And this here is the region. Okay, the lower limit of the solid, and this is x squared plus y squared equal to a squared. All right, and the cylinder goes all the way up and down. Okay, up and down. And now let's draw this other cylinder. This other cylinder here is going to be along the y-axis. Okay? Okay? Y-axis, we're going to have something of the sort, and the cylinder goes all the way there. Alright? And the solid that we want to visualize before integrating will be something like this. Okay? Will be something like this. Okay? This upper part here, comes from this cylinder here, okay? This cylinder here. The upper part, the lid here, comes from this cylinder here. And the lower part, this part here, comes from this cylinder here, okay? This cylinder here, when they intersect each other, we have this solid here. So this is the surface that we are attempting to integrate. And the x is going to vary from 0 to a, okay? And y is going to vary from 0 to a squared minus x squared. Alright? This is the relationship between x and y. And z is the function. Z will vary from this part here, the bottom, this part here, to the function f of x, y. And the function is a squared minus x squared, the square root of it, okay? So this is the relationship between z and x. And to calculate the volume of this word solid here, we integrating the function fy dx dy, and this is the integral in x from 0 to a, and the integral in y from 0 to a squared minus x squared, the square root of it, of a squared minus x squared, the square root of it, dy dx. Okay? dy dx. And now we can simply integrate. We can simply integrate here. If we integrate, we don't have y here. You can see how we integrate it is. We don't have y here. Then a y is going to have to pop up. Then we are going to treat this as a constant, and then a y is going to appear here. Okay? So it is going to be the integral from 0 to a squared minus x squared, the square root of it, y times a squared minus x squared dx, and we evaluate this from okay, we are integrating y first. X varies from 0 to a, and y here we are evaluating, and it varies from 0 to a squared minus x squared, the square root of it. Okay? Could you visualize how to integrate this? And then it becomes the integral from 0 to a of a squared minus x squared dx, and this integration is 2/3 of a squared. But there is a catch here. The cylinder is not this part only. This is the first octant part of the cylinder. We need to multiply it by 8, because we have this part here for negative y, we have the part here for negative x, we have other two parts here, and we have other 4 parts for negative z. So it is going to be 8 times 2 over 3a squared, and it is finally 16 over 3a squared, okay? Alright? This is everything for exercise 5. Let's go to exercise 6 now. Exercise 6, calculate the integral of this function here, ln of x squared plus y squared dx dy over d, where d is the region of the first quadrant, bounded by x squared plus y squared equal to 1 and x squared plus y squared equal to 4. Okay, let's understand the region of integration. We have something of this sort here. Okay, and we have a circumference like this and another like this. Okay, this is 1 and this is 2. Okay, and we are going to integrate here. We are going to integrate here in this portion here. All right, but as you can notice, it is going to be difficult to integrate in Cartesian coordinates. We are going to change from Cartesian to polar coordinates. Okay, and we are going to have an infinitesimal here. Okay, we are going to have an infinitesimal here, which is dx dy. Imagine here, okay, the plane, and we are going to locate it using a vector, which is r. And this infinitesimal here in polar coordinates is, instead of dx dy, it is going to be r dr d phi, okay? Why r dr d phi? And I'm going to show you this infinitesimal here. I am going to pick a very small surface here. It is going to vary here in dr, and it is going to vary here in angle d phi here. All right, and if you prefer, you can use a theta. You can use theta here instead of phi. It is more standard for double integrals. We use phi for cylindrical coordinates. For polar coordinates, we use theta. And to locate this, we need a radius. So it is going to be r dr d phi in the place of xy, okay? And so this is how we are going to integrate this. And we need to understand that the relationship between x and y, okay? And xy with r and theta. We know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. All right? And in the first quadrant, we know that r varies from 0 to 4. from 0 to 4, okay? No, sorry, from 0 to 2, okay? Because the standard form is x squared plus y squared equal to a squared. So a squared is equal to 4, a is equal to 2 here. So r varies from 0 to 2, okay? Here it is 2, and theta varies from 0 to pi over 2. Now we know the limits of integration, we can simply integrate now. And the integral in Cartesian coordinates dx dy is the integral, becomes the integral in polar form, polar coordinates. In this way, r times the ln of r squared dr d theta. We're going to use the power property of logarithms to pass these two to this side here, and we have this form here from 0 to pi over 2, 2 times r ln r d theta. And now we can simply integrate. And if you do not know how to integrate this, you can simply look it up in a integration table or table of integrals, and we get that this is pi over 4, 8 times the ln of 2 minus 3. Okay, so this is the solution of exercise 6. Let's go to exercise 7 now. Exercise 7 now. Calculate this double integral in polar coordinates. To convert this Cartesian form in polar, we need to understand how to convert. And we know here, the exercise gave us that x varies from 1 to 2, and y varies from 0 to x. Okay? I'm going to use this in this way here, the relationship between xy with r and theta will be, firstly we know that there is a limit here, and in this limit x is equal to y. Alright? So we are going to integrate from x is going to vary from 1 to 2 here, okay? The exercise imposed this condition. X is going to vary from 1 to 2, and y is going to vary from 0, okay? Y is 0 along the x-axis, and the limit for y is the function. The limit for y is the function y equal to x. So we are integrating here only. We are integrating there only. And we're going to have a radius here, okay, with an angle, okay, and this is the infinitesimal. And we are going to convert the x dy into r dr d theta, and theta varies from 0 to the function. Theta is going to go in this direction. At x equal to y, theta is 45 degrees. Alright? And we know that x is equal to r times the cosine of theta for x, and we know that x can either be equal to the limits equal to 1 and x equal to 2. So r will vary. R is going to be 1 over cosine theta, which is the second of theta, and r is equal to 2 over the cosine of theta, which is 2 times the second of theta. Okay, this is how r varies. So r varies from secant theta until 2 secant theta. All right, so these are our new limits of integration, and we're going to use them here. So theta varies from 0 to 45 degrees, and r varies from secant theta to 2 times secant theta. And here you see that there is a detail here that x squared plus y squared is equal to r squared. Okay? If we square this, and if we square y, y is equal to r times sine theta. If we square y, add x squared to y squared, you're going to discover r squared. Then x squared plus y squared is r squared raised to 3/2, we get 1 over r cubed r d theta. All right, and we can now integrate it simply because we have reduced this into this by applying this reasoning here, and now we have a function that is a lot easier to integrate. It is a lot easier to integrate now. And you can simply integrate this, and you are going to discover the value of 0.33535. Okay, my friends, this is the solution of exercise 7. Let's go to exercise 8. Exercise 8. Calculate the volume of the solid bounded by the surfaces z plus x squared equal to 9, y plus z equal to 4, y equal to 0, and y equal to 4. Okay? The solid's upper boundary is, z equal to 9 minus x squared. And the lower boundary is z equal to 4 minus y. Okay, the top of the solid is z equal to 9 minus x squared, and the bottom of the solid is 4 minus y. Okay, to find the intervals for x and y, we must inspect the projection. Of the solid on the xy plane. Okay, now we are going to inspect the projection of the solid on the xy plane. The boundary of the projection occurs at 4 minus y equal to 9 minus x squared. And this gives x equal to y plus 5. Okay? And on the xy plane, we're going to have something of the sort. Okay? And here we have y equal to 4. We have y equal to 4 here. and we have y equal to 0. Y equal to 0 is the x-plane, the x-axis. Y equal to 0 is the x-axis. It coincides somehow because this is a plane, this is an axis. They coincide somehow, they intersect, and we're gonna have a function like this, -5 here. And the region over which we are integrating is this. Alright, this is the region over which we're integrating. And this boundary here is minus y plus 5. And this boundary here is the square root of y plus 5. Okay, these are the limits of the boundaries of the region over which we're integrating. This is this boundary here, this is this boundary here, this is the x-axis, or if you prefer, y equal to 0, and this is y equal to 4. Okay, we are integrating over this. And using this, we can calculate, okay, x varies from negative y plus 5, the square root of it, to y plus 5, the square root of it. Y varies from 0 to 4. Okay, y varies from 0 to 4. X varies in this direction here from this to this. And z is going to vary from 4 minus y. Z is going to vary from 4 minus y to 9 minus x. 9 minus x squared. And in this way, we can calculate this by using a triple integral. The triple integral over w of dx, dy, dz is going to be the integral from 0 to 4 of the integral from 0 to 4 is in y. We can choose any kind of order. We can integrate in x first, integrate in y second, but I advise you to integrate last in the interval that has only numbers, and in the interval that depends on the other. For example, this depends on y and this depends on y. X depends on y and z depends on y. So you integrate the dependents first and the independent for the last. Okay? And in this way we integrate last in y, we integrate second in x. X varies from y plus 5, and from 4 minus y, a minus x squared, dz, dx, dy. So this is the order of integration, and if we conduct this, we discover that it is 99.78. Okay, this is the result of exercise 8. Okay, let's do another of triple integration, exercise 9. Let's go to exercise 9 now. Exercise 9 wants us to calculate the line integral of the function x squared plus y squared plus z squared ds over a curve where c is the helix defined by sigma of t equal to cosine t, sine t, and t. where t varies from 0 to pi, okay? To calculate this integral, we are going to use this expression here, the integral of f ds is the integral from a to b, from the extremes of an integral from one extreme to the other, of the application of the curve in the function times the magnitude of the differentiation of the function with respect to time, or t if you prefer. Here, dt. Here, t doesn't need to represent time. It can represent only any kind of a variable. T does not need to represent time here. Okay? And now let's do it. Okay, the function f of x, y, z is equal to x squared plus y squared plus z squared. Understand this function as the mass density in a region. Understand this function here. The key to understanding the line integral is this. Understand this function here as the mass density in a region. Okay? That is density in a region. So there is a region here. There is a region here. For example, and in this region there is mass density. And understand the curve as the helix here as a fictitious wire. A fictitious wire. It doesn't exist yet, but it is fictitious. What we need to do is to integrate the density in accordance with the wire to obtain the real wire. So let me draw this. We are going to have a wire here in a region, okay? There is density of mass in that region, and the wire is fictitious. If we integrate this fictitious wire over this density here, then we are going to have a real object, a real wire. All right? And the derivative of this is equal to the derivative of cosine is minus sine, the derivative of sine is cosine, and the derivative of t is 1. Okay, the magnitude of this is equal to, you develop this is equal to the square root of 2. This is equal to the square root of 2. And we are going to apply this here. Okay, we are going to apply this here. And we're going to get that it is cosine t applied here, it is cosine squared of t. Sine t applied here is sine squared of t. And t applied here, it is t squared. Then the function, the line integral of CF ds is equal to the integral from 0 to 2 pi. Okay? The exercise gave us of cosine squared t plus sine squared t is plus t squared, okay, times the square root of 2 dt. And if we develop this, we get this. Okay, this now a simple integration. This is a simple integration now, and we get that this is 2/3 of the square root of 2 pi, 3 plus 4 pi squared. Okay, this is all for exercise 9. Let's go to exercise 10. Exercise 10 is about another line integral. Calculate the line integral of f dr, okay? These are vectors where f of x, y, z is equal to x, y, z. And the curve is parameterized by r equal to sine t, cosine t, and t, where t varies from 0 to 2 pi. All right? The first thing that we need to do to calculate this is to calculate dr dt, which is equal to the derivative of sine is cosine t, the derivative of sine is minus sine t, and the derivative of t is 1. Okay? So, what can we do here? We have already done everything. And dr is going to be cosine t dt minus sine t dt and dt. Okay? And the line integral of f of r dr is equal to, we need to apply this here. Okay, we need to apply this here. We simply put sine t in the place of x, we put cosine t in the place of y, and we put it in the place of z. So it is sine t, cosine t, and t. And the derivative will be cosine t dt, sine t dt, and dt. And by developing this, we get that the function is from 0 to 2 pi, sine t cosine t minus sine t cosine t plus t dt. Okay, we cancel this with this and we get this from 0 to 2 pi t dt, and by developing this we find 2 pi. Okay, this is everything for exercise 10. Okay, I think we have time for the last exercise. Let's attempt to do the last exercise. Now let's go to the last exercise. If f of xy is x squared y x minus 2y, and the curve is t squared, calculate the line integral of the function over this curve here, okay? So this is how we are understanding this. We are understanding the function as density of mass in a place, and the curve as delineating a fictitious object. And if we integrate this fictitious object in a place where there is density, it becomes real. It ceases to be fictitious and it becomes real. Then we are going to do this, and the t here varies from 0 to 1. Okay? Very nice, very nice. We are going to use the technique. We are going to So firstly, we need to find the derivative of the function with respect to t, which is going to be 1 and 2t. Okay, so dr is equal to dt, 2t dt. All right, and we are going to apply the curve in the function. Okay, so the I is equal to the integral from 0 to 1 of f of r dr, and this is equal to the integral from 0 to 1 of I put t in the place of x, it becomes t squared, and I put t squared in the place of y, and it is times t squared. And in the y region, I put again t in the place of x, and I put t squared in the place of y, and I multiply this by dt to t dt. All right, and by developing this, multiplying this by this, we get this. We get that I is equal from 0 to 1 of t to the fourth plus 2 times t squared minus 3t cubed dt, and developing this we get 2 over 15. Okay, my friends, this is all for this video talking about multivariable calculus. I hope you liked it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!